lecture regarding basics, and it's basically a brief introduction to periodic structures, right? All of you heard about it. I try to do things so that we are able to visualize the things which we have already studied in our undergraduate and the postgraduate courses. So, first of all, let me talk about condensed matter. So, condensed matter means the matter whose energy is low enough that it gets condensed to form stable systems of atoms and molecules, usually in solid. Solid means crystalline or amorphous solids, and liquid. Liquid means mercury, bromine, sodium, potassium, metal alloys, and these all are liquids at room temperature. Right? So this is a very simple definition of condensed matter. So condensed matter means we will study both solids, liquids, right, but not gases. Okay? Let me talk about the physics first of all, because condensed matter physics is basically a part of physics. So physics is what? Physics is the study of nature, and a beautiful effort to search an ultimate equation which describes nature completely. All are searching for equation. If we have an equation, and once we get that equation, and on the basis of that equation, if we are able to describe whole nature, so I think that is the ultimate goal of all the physicists. But till now, we don't have such equation. But closer to that, there is a very beautiful equation, that is Schrödinger equation. I think that's also very beautiful equation, and it tries to answer so many questions once we are able to solve that equation. So this is the equation. I think all of you are familiar with the equation. So first term, it contains 1, 2, 3, 4 and 5 terms. So one, it describes the kinetic energy of electrons, another is the kinetic energy of nuclei. Then next is the interaction between nuclear-nuclear interaction, then electron-electron interaction, and then last term describe the electron-nuclei interaction. Why I am describing this equation? Why I am talking about this equation? If I try to look around, then everything is made up of atoms. And what is atom? I think if I ask in my class that what is atom, then somebody stand up and say, sir, it is the smallest particle, and that's the end of the story, which we have learned in the 7th class. And we have forgotten that after that we have learned so many things. But atom is not a smallest particle. If I go back to lectures on Feynman, its first volume, its introductory chapter, in that it was written that if everything has been lost in this universe, on this earth, and one message is passed to the next generation, and what is that message? Means there is something, and that's very interesting. What is that something? Means when that something is brought closer to each other, they try to attract each other. They come closer, they try to attract each other. But when we are trying to squeeze them into one another, means that something, we try to squeeze them into one another, there is a large repulsion. And we people on this earth call it as an atom. I think it is the ultimate definition of atom. And later on we talk in terms of their constituents, and its constituents are electrons and the protons and nuclei. But in material science we have to deal with only with the electrons, and electrons are only sitting under the influence of protons. Neutrons are not contributing so much. Means Coulombic force is provided to those electrons by what? Coulombic force is provided by nuclei, not nuclei but simply protons. So that's why we are talking about the proton number. Proton number means atomic number. So that's why I am talking about the electron-electron interaction, because one electron is interacting with another electron and nuclei is also interacting with electrons and all are in motion. Nuclei are moving very fast. Sorry, not nuclei, but electrons are moving very, very fast, but nucleus is almost stationary, right? So to solve it, we will apply so many approximations. So that means our ultimate goal is to solve this Schrodinger equation, and this equation is a very beautiful equation. So many people worked on it. First of all, Schrodinger did something, and then in matrix formulation, Drake did a very beautiful things to this, and then Klein-Gordon is also there. So that means what we will do, we have to in condensed matter physics, or especially in solid state physics, because in these codes, whether it is quantum espresso, CS or Min2K, mostly people do calculations for solids or for periodic systems, but not for the solids. For solids, what you have to do, you have to do molecular dynamics, means you have to see the changes in those structures with temperature. Because when we keep on increasing temperature, then solid will become liquid. And when solid will become liquid, it can be seen with the help of an autocorrelation function. But we are not going to talk about that here. We have to simply deal with the periodic structures. So there I have used the GDIS code. Say, this is a three-dimensional structure. It's a two-dimensional structure, and its unit cell is this. Its unit cell is this three-dimensional structure, and its unit cell will be this one, and the unit cell of this is this one. This is a one-dimensional system. So see, a single atom is behaving like a three-dimensional structure. It's also behaving like a two-dimensional structure, and it is also behaving like a one-dimensional structure. And this is because of the periodic boundary condition. Right? What do you mean by periodic boundary condition? Say, I sometimes give an example in my class to my students that what's the meaning of that. Say, if I am sitting in a 10 by 10 by 10 room, it's a closed, and near to me there is another room, right? That is also 10 by 10 by 10, and so on. It's repeating in all the directions like this. Like this unit cell is repeating. So what will happen? I am sitting in a one room, some other person is sitting in another room, and so on. What will happen? I try to interact with that. Either I will call him or her, right? Because the room is closed, I can move only within that room. So I can interact with nearest neighbors, right? And if I can communicate with second nearest neighbor and third, but beyond that I cannot interact. So that means if I try to look at an atom atomic radius is almost 2 to 3 angstrom. So that means if I put an atom in a box of 3 by 3 by 3 angstrom box or 4 by 4 by angstrom box, then, and if I keep on repeating that, that means that is a three-dimensional structure. But if rather than 3 by 3 by 3, if I make the dimension 3 by 3 by 10 or 15, then it can interact only along one surface, but in a direction in which the distance is large, then it cannot interact, right? See here the distance is very large. So when I repeated this structure, then it cannot interact with this. So that means it is a isolated two-dimensional sheet. So this is the idea behind every code, so that we can generate a two-dimensional sheet. A single atom is behaving like a sheet. Similarly, if cell size is this 3 by 10 by 10 or 3 by 15 by 15, then it will behaves like a one-dimensional system. And if the cell size is 15 by 15 by 15, it depends upon how many atoms we are taking, right? So then it will behave as a zero-dimensional system. So this is a very basic idea for every periodic structure. Sorry, every code, DFT-based codes. This is the way we look at the periodicity. So that means we can design a zero-dimensional system, one-dimensional system, and two-dimensional system. So that means, let me consider now a one-dimensional lattice. Lattice means positive ions are there, and around those positive ions electrons are moving. And this is the periodic potential. You heard about it. And interionic spacing is A. Then the potential should look like this. Because electrons are moving under the effect of some potential. They are not free. Right? So periodic potential is defined in this way. Ux plus A is equal to Ux. You have studied this in the undergraduate course. It's a very simple equation. This equation is a very simple equation. You heard about it. And this is invariant under a translation. Right? It will remain as it is, because we keep on repeating the things. And what is the effect of that? This makes the wave function. Wave function means if I take psi star psi, that means I am taking its probability. So that means its probability remain invariant. Here, so what we do to do that? Let us try to understand it and try to appreciate it. You have heard about these equations in your courses, but today we will feel it. Until unless we are not able to feel the equation graphically, that means we didn't understand it. It will take a time. So have some patience. So that means my wave function is periodic. So periodic wave function can be written like this. Psi x plus A is equal to psi x. And similarly, if I multiply with their complex conjugates, that means psi star psi, then it will also remain invariant. This is the meaning of this one. So how this thing can be seen? So invariance of probability density implies that wave function be of general form. So what a wave function looks like? Let me see. Wave function should be of this form. Just focus over this equation. Psi x plus A is equal to exponential iota Ka psi x. Now what is exponential iota Ka? Exponential iota Ka is a periodic wave. Sorry, not a periodic wave, but it's a wave function. It's a wave function. Looks like a plane wave. Means e raised to power iota Ka means either it is sine theta or cos theta. So sine theta or cos theta, we generally treat it like a plane wave. So that means this is a plane wave. When this plane wave is multiplied by psi x, so what is psi x? Psi x is basically a periodic wave. There is a difference between plane wave and periodic wave. Don't get confused. There is a difference between plane wave and periodic wave. Plane wave means it's a sinusoidal wave and it is also periodic. But periodic wave means it need not necessarily be a sine wave. So let us have a look at it. So this wave This is a periodic wave. It's like a square wave. It's a periodic wave. And here it is a plane wave. I think it's not visible to you. It's like this. Let me do one thing. How it looks like. See, it's a plane wave. We call this as a plane wave, and it's a periodic wave. Both are having same frequency. It's a periodic wave. There is a difference between the two. And when these two gets multiplied together, then what will happen? I am getting this wave, this wave. Their product is like this. So that means if we try to look at the nuclei, nuclei will be somewhere here, and around it the probability will be somewhere here maximum. Probability of electron will be here. It's like this. Sorry, here the probability will be maximum. If I try to look at the electron, then its probability will be maximum near the nuclei, and then it keep on decreasing like this. So that's what I am getting out of it. This is the idea behind the block functions, which we have studied in the condensed matter physics. So that means I have plotted here periodic wave, block wave, and the plane wave. I used GNU plot, and I have taken script from somewhere internet for this. See, this is the block function. This is a block function. So, is everything clear to you that what is happening inside the code? And this will take care of the periodicity. So, up to this, any question? I think everything is clear or nothing is clear. There are two possibilities.
Please show this block wave clearly. Which one is block wave?
Block wave is this one. Yeah, this one. This is the block. Yeah, very block wave. It's the product of these two. Let me go back to the board. So if I multiply these two, then the block function, sorry, the block wave which I am getting, it's like this. It's like this. It's like this. Right? Let me do one more thing. This is block. This is block. Right? And this is, let me take another color. And this is, and this is our periodic wave. This is periodic wave. Right? This is periodic wave. It's like a square wave. Basically, idea came to my mind. Let us see that what is a block function. Let me try to feel it with the help of some graph plotting tool. And I think nuclear is the best tool to feel these things. So many things can be visualized. We need not to do so many complicated programmings. Because difficulty with us is that we have to learn so many things. Computer, graph plotting tools, Lect, so many things, experiments. We have to much more familiar with the equation. Then nuclear is the very best tool. And this is a plane wave. This is plane waves, right? Is a plane. Plane wave is any sinusoidal wave. Okay. Now let us come to another. What is the consequence of this periodic potential and block waves? When the role of periodic potential and block wave came into existence, this equation will emerge out. A lot of mathematics is there. I am not talking about that mathematics. And this is a very beautiful equation. I have put some values and then plotted the things. This green colored is basically it is cos. It is basically this part which I plotted. Sorry, it is this part cos Ka. This green colored graph, right? And another one is this one. Sum of these two. That means the sum of two terms is equal to some third term. But when I plotted it, what's going on? They are not matching. Something is equal to some other thing. What does that mean? At least they must match exactly what they are not matching. When I look at these graphically, what's going on? Mathematics is over here. But the role of physics came into existence here. So how physicists look at this equation? That means something is equal to some other thing, so that means some values are allowed and some other values are not allowed. Here the idea of forbidden gap came into existence. See this. See, if I try to look at it, so that means take this so that I can explain things to you. See this. So that means only the values between -1 and +1 are allowed and rest of the values are not allowed. This is the shape of this wave function. It looks like this. So that means these values are not allowed. Not allowed. Not allowed. Not allowed and not allowed. From here the idea of this forbidden gap will be emerged out. As I understand. I may be wrong. But it seems like that, this to me. Right? So this is the thing. So here we are getting the band gap. So this I have obtained from the internet. Reference is the Wikipedia for this. So this is all about it. So I think up to this everything is clear to you. This is a way to look at the forbidden band gap. So that means the band structure, actual band structure, is basically the result of the periodicity and the block function. Means when we incorporated the periodic potential in the picture, because earlier we look at the free electron gas model, that can explain few things, but most of the things cannot be explained on the basis of that. Then people thought that no, electrons are not free. They are under the influence of some potential, and potential should be periodic. So when they incorporated the periodicity of the potential into the picture, the idea of band structure will be merged out. Now what is band structure? We try to look at the band structure. Band structure is basically the graph between energy and K space, E versus K graph is the band structure. Right? So that means we have to understand the reciprocal space or the K space. So what is a reciprocal space? As I feel that reciprocal space, people call it as a Fourier space, they call it also a K space, and it is the mathematical manifestation of diffraction pattern, right? So I have taken some Python script from somewhere and I did little experiment. So here I have taken a slit width in the Python script 208 micrometer, and then distance from the center is around 0.001 unit. This distance from center means I am talking about this distance here. Means this is first peak, central peak, and the first peak, the distance between these two. I am talking about this distance. Means when slit width is this 208 micrometer, I use the Python script for this. Then earlier it is 208, now it is 131 micrometer. Means it gets reduced. Slit width gets reduced. What will happen? This distance will become larger. The maxima shift, means the distance between the two maxima, it shifts, right? That means when slit width decreased, the separation increases. There is a reciprocal relation. See here, it's again increased. And this is a overall conclusion of all these three things which I am writing here. Means with the decreasing slit width, the separation between center maxima and first order maxima decreases. Means they have inverse relationship. That's great. Let's go to the laser lab. I did the same experiment with different diffraction gratings, and I calculated their grating elements. My PG students was somehow maybe here who did this experiment. I don't know who did this experiment for me, but for different grating elements, I am getting this one. Right? Same, which I am looking with the help of a Python script. Same thing I am looking with the help of this diffraction grating. Same thing is again. So that means there is an inverse relationship between the real and the reciprocal space. What we do in X-ray diffraction, I am not an experimentalist. That means when separation between atoms gets increased, the peaks comes closer, intensity peaks comes closer, and when atom comes closer, peaks gets away from each other. That means the pattern which we are observing on the screen or X-ray diffraction, it is basically Fourier space. K space means it is the Fourier space. Means similar equation we are looking in the Fourier space. So here it is a single slit and it is its Fourier transform. It's a single slit and it is its Fourier transform. And if slit size gets changed, then these things we will observe. Because Python script is nothing but it is the Fourier transform of the single slit. But it's a mathematical modeling. So that means there is an inverse relationship. See, it is the real space and it is the reciprocal space with green color for three-dimensional space. So up to this, any question? Quick question?
What is the reason behind this inverse relation?
Inverse relation?
Yes, between the separation between atom and diffraction pattern.
If we go to the say when people see diffraction with ordinary light, then they also studied that there is a inverse. It's like a shadow like things when object is when seen light is thrown on somebody something when we light through on slit, say people observe first of all diffraction with light, right, and then they see what happens to the pattern, diffraction pattern, when we keep on observing with the different slits of different sizes. Then they saw that there is an inverse relationship between them. It's like when we are closer to the source of light or away from the source of light, then shadow will increase. It's like that, but here the wave nature is also coming into existence, and because of that they observe something and then they try to find a mathematical model for that. And same thing people use for the X-rays also, because X-ray is also like a wave. So when wave is passed through that, so similar type of things they are observing for the X-rays. As we do the experiments in lab to find the thickness of human hair or the size of a slit using the light, so same mathematics will be used to perform the calculation for it. Right? So this is the idea behind. Means when what we do in physics, as I think, we keep on observing that what is going around us. When we keep on changing one parameter and another parameter, and things will change. And how those things will change, we will try to find out the mathematical model for that. Right? So that is basically its mathematical manifestation is sitting with the Fourier space. So I think this was the reason behind it. So this thing will help us to decide the K mesh in every DFT code. Right? And this is the reciprocal space of this real space. So there are two things with us. One is the real space and another is the reciprocal space. And another idea will also came into existence, that is the primitive cell. Primitive cell means a cell in the real space having minimum volume, and with the repetition of that, we can repeat whole of the crystal, right? And symmetry is also the minimum volume space in the reciprocal space. And this is the Brilliant zone of what? This is the Brilliant zone of BCC lattice, about which I talked about here. Let me draw these things now. That's how things looks like. we talk about primitive cell and then its reciprocal space, right? Let me draw. This is a real space, right? Now what I will do, I want to draw what? I want to draw a reciprocal space for it. Reciprocal space means what? Say if I take origin will be here, or I can take origin here. I take the perpendicular distance between these two, right? And if I take perpendicular distance between these two and take their reciprocal, then it's like this. Say, and let me assume that the distance is, let us suppose that distance is 0.5. Let us imagine that. In 0.5 unit is the distance of these two in the real space. So what will happen? It will become 1 over 0.5, it will become 2. I am just giving you just feel of it. So that means the distance between these two is this, but it is its distance will be like this, right? And similarly for this, it will also increase up to 2 times, and it's also increased up to 2 times. And then I can complete with these 3 unit vectors in new reciprocal space. Why I am talking about this? What is happening in our structure? Because we have to take the K mesh, because when we plot a energy level diagram, E versus K gram, we have to integrate in the reciprocal space, and then we will get the band structure. So what is there in that? Say, I talked about 2-dimensional structure, and I talked about in 1 dimension, the cell size is very large. Say, cell size is cell size is say 3 by 3 by 15 angstrom. This is the cell size. So that means along these 2 direction periodicity is there, and along this direction there is a vacuum direction. So when I take reciprocal of all these 1 by 3 is 1 by 3 and 1 by 15, this value is very, very small. And we need a very less number of K points along this direction in which vacuum is there. So K Moncost path which we will take, in general 10 by 10, you will see in your code 10 1 1 1 10 1 1 1 1 10. You will take it for what? We will take it for the bulk material. But when you have to switch over from bulk to 2-dimensional material, what will you do? You have to take 10 into 10 1 1 0 10, sorry, not 0, it is 1 10 1, then 0, sorry, it is 1 1 1. Means along vacuum direction you are taking 1 K point. Why we are taking 1? Because along this direction cell size already has been reduced in the reciprocal space. That's why we are taking a lesser number of K points. Because when we take a large number of K points, the computational cost will become very large. So that means 2D it is sufficient 10 by 10 by 1. In quantum espresso, sir, it is not written in quantum espresso like this, right? K Moncost path. It is like this 10, 10 and 10, right? For bulk. Yeah. In siesta it is written like this, but in quantum espresso it is written like this. But when vacuum is along, say, let us assume that vacuum is along Z direction, then you have to take K mesh 10, 10 and 1. But when vacuum is along Y and Z direction, means it is for 2D material. For 1D material, if it is 10, 1 and 1, because in 2 direction vacuum is there. And when you have to do it with the 0 dimensional systems, then you have to choose 1, 1 and 1 came on cross back. So this is a very tricky point in April code, right? And let me go back to again my presentation and yeah. Now see, it is the brilliant zone of what? It's the BCC lattice, right? And here, these are some high symmetry points are there in it. These are known as, center of it is known as gamma point. And here, it is the corner of what? It is the corner of these square faces. This is known as P. And gamma to P, this line is known as lambda, means high symmetry line. So that means you must familiar with what is the meaning of high symmetry point and what is the meaning of what? What is the meaning of high symmetry lines? There is a book by Paragosini on optical properties. You can see all these things in detail. That even you Google them for every structure, means whether it is a simple cubic FCC, BCC, different lattice high symmetry points are given. So you should be very particular about this choice of the KMH, choice of the high symmetry points. When you are doing some calculation with any DFT code, you should be very particular about it, right? And the idea of real and the reciprocal space I have given to you, and how this vacuum will affect these things. So this is a very important point. So with the help of X crystal, you can see these points also. And their nomenclature is standard for various lattices. So you should be very particular about that in every code. So I think this is all about this lecture. Now session is open for discussion. Any question? No question? Then I should ask question. Thank you.